Hello everyone, and welcome all on Data Phoenix webinar. Today with us Shishar Patil. He is PhD student at UC Berkeley, and we will talk about Gorilla project, which is designed to connect large language models with various services and applications through APIs. So I give to him microphone.
Thank you, Dimitro. Thank you for having me here. So let me share my screen and then we can get started. Uh, Great. Okay. So, like Dimitro mentioned, today I'll be talking about Gorilla, and I've kept the talk to be slightly more technical and also like probably give you the insights. The hope is that post this talk, you'll be like, okay, how do I adopt some of the techniques that we have into your own work? And if you have any questions at any point of time, feel free to ask, and I'm more than happy to take them as we go. And before I begin, all the work that we have done is open sourced, and at Berkeley we believe in like building the project, maintaining it. So if I encourage you all to take a look, and if you have any feedback or comments, it's welcome as well. So this is joint work with my collaborators, Tianjun and Joey from Berkeley, and Jin from Microsoft Research, and I'm Shishir. Okay, so on the agenda today is first, I'll try to look at what's the Berkeley view on LLMs or how we think LLMs will evolve. And then I'll try to address what I think are some of the two interesting questions in the LLM space. One is how do you do retrieval aware training? And the second one is how do you measure hallucination? And finally, in through the process, I'll show you some demos and hopefully convince you that there's a system that actually works. So that's the agenda. Let's get started by taking a look at how people use LLMs today. All right. So on the left-hand side, you have all your favorite LLMs. This includes the OpenAI, Anthropic, Azure, Claude, and then so on and so forth. Then you, as a user or as a developer, are at the center of this. And on the right-hand side is the entire big world. Now, the way you might think, or if I were to graphically represent the way you use your LLMs today, it would be something like this. You first prompt your LLM, and like I said, there's one too many of them, and then you get a response from your LLM. This could be like, oh, how do I install CUDA on my machine, or how do I do X? And the LLM tells you what to do. Now, I've represented this as a zero-shot scenario where you ask a question, get a response, but this could be multi-shot, right? Like you can keep asking some questions and keep refining the answers as you go. And by the way, there's a whole bunch of tools that help you do this, like LangChain, so on and so forth. But fundamentally, when you get the response, it's your responsibility to now take this response and then perform some action on the world. And this could be like, oh, I got a bunch of code from my ChatGPT. Now I have to go and copy paste that code. Or like ChatGPT asked me to click these set of buttons on this particular website. Now I need to go and do that. And then you get a response from the outside world, right? So this is the lay of the land for how you interact with LLMs today. And again, even the action and response can be multi-round, and then you can go back and forth multiple times. What we want to address or answer is the following question. Instead of doing this, can we flip this around? Can we put the user on the extreme left, right? And so the question you're trying to ask is, can the LLMs themselves introduce effects into the outside world? So as a graphical representation here, you would ask a prompt, and now the LLM is going to go and perform this action on the world, and you're then going to get a response, and then it's going to return it back to you. So why do we want to do this, right? Because humans are good discriminators, they're not good generators. So let the LLM do, interact with the world and then show you what's done, and then you're like, okay, I accept or I reject. And some examples of, I'll try to ground what this action response is, but this is a scenario where your LLM now has to not just talk to you, but also talk to the outside world, right? And we thought of this paradigm sometime around the end of November, December last year, when we were like, look, today a lot of people are using LLMs as chatbots. Now, chatting is a great demonstration of the technology of LLMs, but the technology itself is more fundamental, right? So we thought of this as a very powerful tool. By this, I mean LLMs. And one thing we know about tools is that tools become more and more powerful in two scenarios. One is when you allow the tools to be used by more people, and two, when the tools can talk to other tools, right? What we're trying to enable is the second phenomenon. How can we make tools talk to other tools? And if you think of LLM as a tool, and then you have all the other different computer systems as different tools, how do they talk to each other? And one thing we know in computer systems is that the way different software systems talk to each other is through well-defined API calls, right? So where you ask a question, there's like a response and a promise. So you have a promise, if I call this API, then this happens, and you get that as a response. So this was the motivating idea, which is that can we programmatically train these LLMs to now interact with the rest of the world, and with the world here, I mean software systems through APIs. So that's the idea. So we have so far like spoken mostly abstract, but to ground it in a good example is to say, oh, we all are machine learning researchers, and some of us are practitioners, and we're like, I would like to have an 800 GPU in East US. You can have a different region, or you could pick the GPU that you like. And now, can the LLM go ahead and figure out, oh, do you have quota for this? And figure out, oh, is there availability for this? And if so, can it start the GPU instance and return the SSH key to you? And the LLM we trained to do this is called Gorilla. So Gorilla is an LLM that's trained to now take a user's needs in natural language and then determine which action to perform on the world and return the response to you. So in this case, Gorilla would choose, say, an Azure API to, prompt and respond with your LLM. So you prompt your LLM, hey, I want an 800 GPU. Gorilla, which is the LLM, is going to go talk to Azure, get an 800 GPU, and then return the SSH to you. So this is one example of how, if you were to think of LLMs interacting with the world, what would that look like? Now, I give you one example of Azure, but obviously there's a whole bunch of APIs that you can support, right? And this is a growing field, but for now we support all the hyperscalers like Azure, GCP, AWS, and a lot of users were like, hey, we want Kubernetes. Kubernetes is hard to use, so we support Kubernetes and Stripe, Hugging Face, PyTorch, TensorFlow, so on and so forth. If you have any APIs that you think we should support, please let us know. And we have a vibrant open source community that's helping us get there. So this is the high level idea. Now, before I proceed and tell you how we make this work, let me actually show you a demo and hopefully convince you all. So this is a command line. Let me try to zoom in a little. And you could ask something as simple as Gorilla list all my GCP instances, right? So this is a natural language query that I'm going to ask into my command line. And then what we do is Gorilla is going to go ahead, run the command in the background, and then show you a bunch of commands that you can use. So I'm going to pick the command, which is going to execute, and then it's going to show you that, hey, look, here are the set of GCP instances that I have, some of them terminated, some of them running, etc. Now, we have an LLM that can write APIs. The command line is one modality to use this, but you can think of multiple other modalities, right? So this is one example. The other example that's pretty popular is, so here I'm going to show you how you can integrate Gorilla with LangChain to actually accomplish tasks back to back. So this was done with our collaborators at LangChain. So you go ahead and you install the dependencies, and the only thing that you do is you call the OpenAI chat completion API, but instead of using their backend, you can hit the Gorilla backend. And by the way, this is just a hosted service, but all of our models are on Hugging Face, so you could also directly download the models from Hugging Face and use it yourself. Now, suppose you have the question, hey, I would like to translate from English to Chinese, right? A simple question. What Gorilla does is that, when you call the chat completion API, the first thing it tells you is that, hey, look, this is NLP. The API call that you really need to do is, this pipeline translation E into ZH, and here's a Helsinki NLP model that we're going to be using. And there's some interpretability aspects of it where we explain why we're doing what we're doing. And then this is the complete code that you can now, or like a snippet of code that calls this API, right? So here, for example, you're saying, hey, what are the key differences between renewable and non-renewable energy sources? And can we translate this to from English to Chinese? Now, this code is readily executable. So this is a simple Python exec command, right? So execute this code, and then you see the response here. So there's a bunch of downloading the models from Hugging Face that's going on, and then you get the translation from English to Chinese of this particular sentence. And by the way, all of this code and even the command line is open source. You can install the command line with pip install Gorilla CLI. That's about it. So it's available as a pip package. And similarly, you can now think of integrating this chat completion API endpoint into your own service. Now, hopefully, please don't use this for serving. This is just a small hosted service that Berkeley is providing, but the models are available. So you could download the models or host your own models and use it as well. So that's, hopefully I've convinced you that Gorilla works and is usable, and, encourage you all to try it. So now let's talk through how does Gorilla work, right? Like how are we able to actually enable this and get this to work? By the way, any questions so far? Dimitri, I can't see the chat. So if you have any questions that you want to surface, I could take that too.
No, for now we don't
Okay.
have questions. So if someone has a question, please ask in the chat on the YouTube channel, and we will answer for them if you have the question. Yeah.
Awesome. Okay. So going ahead, um, let's talk through how Gorilla works, right? So one of the key questions that we try to answer with this work is that how do you mix fine tuning and retrieval? And I use fine tuning to include instruct tuning, RLHF, and all the post pre-training techniques. And retrieval is in reference to all the RAG and other techniques where you're trying to like augment your prompt with relevant context to help the model answer better, right? So this is the idea. This is the question. And the hypothesis, or at least the one that most people roughly subscribe to, the view of the world is that fine tuning is to augment the behavior of the model. And again, like I said, fine tuning is used to mean both RLHF and instruction tuning, whereas retrieval is meant to introduce new knowledge to the model, right? So it's like, if there's some new data that comes up, then can we use that through retrieval? Whereas in fine tuning, you're trying to like make it spit out the answer in the way you want it to. What we find, at least in Gorilla, is that fine tuning is actually quite remarkable at both behavior and at knowledge. You can bake in new knowledge post pre training as well. Now, except there's one problem, right? Uh, Knowledge or data is timely, so freshness of data is important, and so you might still want to use retrievals. Except retrievals are inaccurate, right? Uh, it's, I'll show you some numbers with all the popular retrievers out there today. But it's that retrievers may be accurate maybe 70 or 80% of the time, which may look like it's good, but it's actually pretty bad, which means you're wrong one third of the time. And by the way, what do I mean by accurate is for retrievers, the way you measure them is by recall at k. So you say if I were to give like recall at 3 means if I were to give you a choice to like give me 3 answers, at least in one of them were you able to get it correct. So even for something like recall at 3 or recall at 10, retrievers are actually quite inaccurate. So the solution that we have is called RAT, which is retrieval aware training. So the idea for RAT is pretty simple. If there's like one line summary of RAT, it's this. We know retrievals are inaccurate. Can you now fine tune the model to be aware of this inaccuracy? So can you fine tune the model to actually use or ignore the retrieved context, right? So that's the key idea over here. So, and you're able to do this by introducing both correct and incorrect retrieval results during instruction fine tuning. And what this does is it ensures that the model is robust to low quality retrieval, which is the goal. Remember, retrievals are inaccurate. So how do you make the model robust to low quality retrieval is the goal. So I'll hopefully it becomes more clear when I explain with an example. But if we were to visually represent this, there's been this debate about fine tuning versus retrieval augmented generation. We're saying, hey, look, it's not about one or the other. It's not even about the balance of the two. Typically, when you say it's not one or the other, people tend to think, is there a balance? The answer is not, oh, use this sometimes, use the other one sometimes. It's use one for the other, right? So, like I said, here's an example, and probably with this, we can understand this better. So here's a user's prompt. The user's prompt is, I'm an engineer at Uber, and I need to find an API that can classify pedestrians, cars, etc. from an image of the scene. Give me a Python program that calls an API in Torch Hub, right? Pretty simple. Now, if you were to use a retriever, here's what the retriever would give you. It says object detection, the framework is PyTorch, and I'm going to call something called hybrid nets. Uh, this is a scenario where the retriever took your prompt, did a cosine similarity with all of your APIs in your database, and then retrieved this particular API. So we do a few things here, right? The first thing with retrieval aware training is you're trying to ask this question: is this the relevant API? Was my retrieval accurate, or was my retrieval coming up with absolute irrelevant APIs? Is something that you want to try to answer. And once you ask this implicit question, so this is a one bit implicit question. Your LLM is not going to tell you, oh, this is the right API, or it's not going to tell you, oh, this is the wrong API, but it's going to implicitly answer to itself: is the reference API that you generated through retrieval aware generation relevant to the user's prompt, or is it irrelevant to the user's prompt? In this scenario, it turns out to be relevant. So I'm going to respond to the user's prompt incorporating this API, right? Get the prompt, retrieve your API, check if it's relevant. If it is relevant, incorporate this prompt as you answer the question. If it's irrelevant, then you drop the prompt as you answer the question. So that's the key idea. Now, obviously, in the training time, we also use wrong APIs, right? So why do we do this? Is because your retrievers can be inaccurate. Remember? So what if the retriever was inaccurate and it gave you a PyTorch phase sequence API? Now, this is a translation API, right? So using this to identify pedestrians or cars from an image is not really practical. So what Gorilla the LLM does is that it's been trained to ignore this API and instead answer the prompt from the knowledge that's in its pre-training or in its fine-tuning, uh, or that we bake in during its pre-training or fine-tuning stage, right? So in this case, even though we gave it the wrong API, it was able to discard the API and actually answer the retrieved information from the knowledge that was baked in. So this is the idea, right? Train the LLM to use the retrieved information or to reject the retrieved information by retrieval aware training. Any questions on this?
We have one question about the list of APIs which Gorilla support.
Yeah, so that's a good question. And so for now, we support, like I said, all the hyperscalers: Hugging Face, Torch Hub, hyperscalers, Azure, GCP, AWS, and all the top machine learning repositories. So this includes Hugging Face, TensorFlow, PyTorch, and also a bunch of your Linux commands. This includes AWK, sed, your Python environment, things like Conda and virtualenv, Git, GitHub related stuff, and also Kubernetes, Stripe, and we're adding support for Salesforce, ServiceNow, Datadog, etc. In the roadmap.
Yeah, and
Yeah, so it's a growing basket of APIs that we support, and we also have. I'll talk about this later on, but we have something called the API Zoo, where you can contribute APIs if you feel like, hey, look, here's a set of APIs that I think should be added, and then we'll take those APIs and we'll train the Gorilla model so we can also serve that.
yeah, and one more question about how the Gorilla will answer when the retriever context is wrong.
How will Gorilla answer when the context is wrong? So, like, are you referring to the slide that I have up here? Uh, I, probably, if my interpretation of the question is, what if the reference API is wrong? And so that's what Gorilla does, right? So you ask the question, the user has a question, the reference API is wrong, then Gorilla will implicitly discard the reference API and then answer the question based on the data that it has it from its pre-training step or from its fine-tuning step, right? So we fine-tune the Gorilla model across all of these API documentations. So it's aware that, how to answer this question, even if I did not have retrieval.
Good. For now, the
Okay,
questions is ended.
perfect. All right. So this is about the retrieval aware training. Now, this is a recipe that we use for Gorilla, but there's nothing particular about API. So you can think of using retrieval aware training even for your even for your post-training recipes that you have if you're trying to fine-tune language models. Okay, with a slight change of tone, the next thing that I want to do is, probably urge you all to think about how much do you think GPT-4 hallucinates? And the reason I'm asking you to do this is when you ask this question, the responses that I get is usually like, oh, a lot or a little, or like, less than 3.5, more than 3.5, similar to Claude. Now, what I want you to, highlight is that a lot of these answers are not quantitative. right? They're all qualitative, they're all relational, some of it is mostly opinions, but there's no real way to measure hallucination. And that's what we wanted to solve. And one thing that we do with Gorilla is introduce a metric that you can use to measure hallucination. Now, I want to be pretty precise in what we claim. This is not generalizable, right? This as a metric would not work if I were to ask you, oh, can you compare hallucination for a general purpose audience, right? So, for example, if I were to ask you the question, when was Mike born? Well, there are a billion mics in the world. So if the LLM comes up with any answer, there's no way for you to tell if it was correct or wrong. Like, how do you know if it's making stuff up or it actually exists, right? So, for example, when was Michael Jordan born? Well, are you talking about Michael Jordan, the professor at Berkeley, or Michael Jordan, the basketball player? Uh, so, given that there might be, unspec questions, it's hard to measure hallucination. But with APIs, we can actually measure hallucination. And here's how I'm going to tell you to do. I'm going to teach you how you can do that. And the idea is called an abstract syntax-free subtree matching, right? So for example, consider this API. This is the API that I get. It says torch upload by torch vision, densnet 1 to 1, which is the name of the model. And there's an optional argument that says pre-trained equals true. The first thing we do from this is we build a small subtree, right? So this subtree includes all the calls and the arguments uh, for this API. And by the way, I should have mentioned this before, but when I say API, I'm not referring to just Python, right? So this could be RESTful APIs like HTTP, GET and POST calls, or it could be GraphQL APIs, it could be SQL, it could be Python, so on and so forth. It could be anything. We support pretty much any API. So once you have this API tree that you build, so if it is a RESTful API, this would be like the base URL plus the arguments in your header and plus the arguments in your body. The next thing that we do is we have already pre-built a database of all the APIs that's available, right? Now, the good thing about APIs is it's very publicly available and it's easy to access. Some of you might have heard of all the legal issues with respect to training data for LLMs. Now, APIs is different because people want you to use their APIs. Like if you use Stripe APIs or Adyen APIs, Adyen and Stripe make money from it. So they have an incentive to make you use their APIs. And so that's why you get very clear documentation. There's open API Swagger files, multiple specs where people expose their documentation and their tutorials on how to use their APIs. The other thing to keep in mind is that these APIs you cannot make up on the fly. Like if Stripe does not have an API, you can't just call that API, right? So it's like it's very well grounded. And with this, we are able to ask a simple question: oh, is my tree on the left a proper subtree of my set of API database? And if it is, then we tell there's no hallucination. Now keep in mind, I'm making no comments on accuracy. You may be calling the densnet 1 to 1 to do a translation task, in which case you're wrong, but you're not inaccurate. Um, you may or may not be accurate, but at least you're not hallucination. So we like to distinguish hallucination from accuracy. And here, all this metric is doing is teaching you how you can measure hallucination, right? So, and pre-trained equals true is an optional argument, and hence we don't compare against that, but that's an implementation detail. But here's the high-level idea, right? And with this, what we're able to do is actually give you a very clear metric on is there hallucination or is there no hallucination. Like I said, this is, it works pretty well with APIs. It's unclear how well I think there's some generalization into code. It's unclear if you can generalize it beyond code and APIs into like, say, natural language question answers. Any questions on hallucination?
No, for now, we don't have questions.
Okay, perfect. So let's look at how well does Gorilla perform, right? So here's a prompt. The prompt is help me find an API to convert the spoken language and recorded audio to text. Now, if you were to ask the same question to GPT-4, you would see that it would hallucinate. And Claude comes up with a library that's not hallucinated, but it's wrong for this particular task. Now with Gorilla, we're able to not just not hallucinate, but also get the right library. So this is obviously a cherry-picked example, but if you were to look at how well does Gorilla perform across the board, right? So if you were to take a big data set, how well does Gorilla perform with respect to accuracy and hallucination? So here's the graph. You want the y-axis to be higher, So higher accuracy is better, and you want the x-axis to be lower. So lower hallucination is better. So you want to be roughly in this space, right? Now here I have zero shot comparison. Zero shot means you ask the question, get the response. There's no retrievers involved. And we compare this across open source LLMs like Llama and also closed source LLMs like GPT 3.5, GPT-4, and Anthropic's Claude. And one thing, the key takeaway is that Gorilla beats both open source and closed source LLMs in terms of accuracy and hallucination, right? So we are able to be more accurate while also reducing hallucinations. So think of this as higher precision with lower recall. Now, this is in the zero shot scenario. You might also ask the question, hey, what if I augment my LLM with retrievers, like you mentioned? So here I'll show you two. This is GPT Retriever, which is today the state of the art retriever, where you basically use text embedding 002v2 from OpenAI, and then you use cosine similarity to identify which document to retrieve. And Oracle Retriever is the one where, if God were to give you the exact API call to use, how well can you use that API call, API documentation inside your prompt to answer the question? Now, in our paper, we also compare with BM25, which is very popularly used. But this is basically the spread, right? And from the spread, you can see that Gola performs pretty good, actually, even when you compare it to closed source LLMs. And by the way, Gorilla is just 7 billion model. So all the comparisons here are for Gorilla 7 billion, Llama 7 billion. And obviously, we don't know what the closed source models are, how big are they. Okay, so this is comparison with some of the closed source models and open source models on how well does Gorilla perform. Now, what I've spoken to you so far is great and works well when you have a closed set of APIs, right? And as we presented this work, some of the feedback that we got was like, but hey, APIs evolve. APIs evolve way more frequently than how often you can train your LLM, right? And a lot of people think training LLM is hard because of it's very expensive, which is true, and you don't have access to GPUs, so on and so forth. Yes, but an even interesting phenomenon is you don't want to keep fine tuning your LLMs very frequently because testing is so hard. Like evaluating LLMs is something that we still, as a community, don't have a good answer on. So, how do you know if you were to do a few more epochs on the LLM that it hasn't deviated from its expected behavior? And how do you make sure that it's nice and smooth across all the corner cases? So, given how hard evaluation of LLMs is, you tend to reduce your training. By training, I mean both fine tuning and pre training of your LLMs to once every 6 months, maybe more frequently, maybe monthly, but no more than that, right? But your APIs may evolve way more frequently than that, sometimes even multiple times a day. So in these scenarios, how well does Gorilla perform? So, we call this test time document changes, is that since we have a retriever, if I were to change the documentation of the API in the retriever, is the model able to capture that as well? So, suppose this is the base model that you have. You trained your model to use FCN, a fully connected network with ResNet 50 backbone. And in test time, say they updated the model, and this is you updated the model from FCN ResNet 50 to FCN ResNet 101. So you're basically changing the backbone. You're making the model slightly more powerful. Think of this as V1 and V2. So if you have the V1 on the left, V2 in the center, then what you can see is that Gola is actually able to adapt to this. It's able to adapt from FCN ResNet 50 to 101. And what I mean by adopt is that the model is able to reason that, hey, look, I've seen ResNet 50, I've seen ResNet 101. So probably when the documentation changes to ResNet 101, it's probably trying to update its backend model. But suppose if you were to say, hey, please use FCN ResNet 79, then the model may go, well, wait a sec. I've seen ResNet 18, 50, 101. I've never really seen ResNet 79. So, is it possible to have an FCN ResNet 79? And this is all a distribution of confidence scores, and probably the model will be like, hey, I'm either going to accept or reject this API change, and then either go back to ResNet 50 or go back to ResNet 101. So this is where you're updating the versioning of the model in some sense. You could also have a scenario where you change your repository, right? So this is you decide to move from one repository to other, from PyTorch Vision to, say, NVIDIA Deep Learning Example Storage Hub. So I'm giving a lot of machine learning APIs as example because hopefully it's something that all of us have used and can appreciate day to day. But Like I said, Gorilla supports a whole bunch of different APIs for both the low code, no code, and the the developers sort of spread. So here's some examples to show you that even if you train the model just on the default response on the left-hand side, as you update or you version your API changes, the model is able to adapt to that even at test time. So, okay, this is the fun part. So we have open source Gorilla. It's been a couple of months, and the response has been pretty encouraging. Right. So we have a Discord server. This is probably one of the best compliments I've got, where it says, "This is the next best thing to slice bread." Right. I don't think we're there yet, but that's we have been on the top of Hacker News multiple times by now. There's a growing open source community and adoption, but more critically for us, right? Outside of the popular press, both internationally and domestically, a lot of AI researchers and thought leaders in the field have endorsed Gorilla and think this is a step in the right direction. So that's been pretty encouraging for us. And Gorilla is also, we have a small hosted service where it's like, if you cannot run the model, just use this Google Colab with which you can access Gorilla. And we have had more than 300,000 invocations in the past 2 months. I need to update the numbers, but it's not just uh, it's not just a novelty factor. People are constantly using Gorilla in their day-to-day lives. So this is the high level impact. And yeah, like I said, it's an open source effort. It's all Apache 2.0, right? So your lawyers are going to allow this. You can use Gorilla today. You don't even have to tell us, but you can adapt Gorilla to your own set of APIs. You can take Gorilla and say, hey, like I have this documentation. I have a bunch of users who want to learn how to use this APIs. Can I now train my own Gorilla for my set of APIs and then serve it to the user? So you could, think of that as well. Okay, so with that, we're coming to the conclusion. So, I spoke about Gorilla and how the goal with Gorilla is to connect LLMs with massive APIs. And we're able to do this by two key contributions research wise. One is retrieval aware training, or RAT, which helps Gorilla adapt to frequent changes in APIs. It also trains an LLM to use retrievers, and how do you be robust to low quality retrievers. And finally, Gorilla is able to improve accuracy and reduce hallucination. And we also presented with a metric on how you can actually measure hallucination when it comes to API calls. Yeah, and with that, I'd like to conclude. And if there's any questions, I'm more than happy to take them.
Yeah, thank you for this overview of Gorilla. We have more several questions. Why you don't use Crawler for get the information from the internet about API and use it for growing your APIs?
Yeah. So we don't want to blindly go and keep crawling multiple APIs, mostly because it's an academic project. So the idea is that the moment you do this, you run into issues like, oh, do some websites let you crawl? Is there a legal aspect to that, etc., that we don't, as an academic project, we don't want to answer. But so that's why we say there's an API zoo, where if you as a user contribute your APIs, then for us it's more clear, at least as a GitHub handle who's contributing their APIs. And it's also a signal of which APIs do people care about, which ones people don't care about, so we can prioritize and use that. And training is expensive, so we can use our resources more efficiently.
Okay, I understand. Yeah, good. Thank you for this presentation. I invite all to join our Slack channel and continue the discussion about Gorilla. See you all on our Slack channel, and see you all on the next webinars. Thank you that you was with us today.
And thank you, Dimitro, for having me here. It was really fun. Thank you.
Thank you.